The camera died. So what I was saying is we have this maximum static friction of 400 newtons. So if I only push it at 344, that is not enough to overcome this force. So it's not going to move. So D. Now, some of you are saying, well, if it's not going to move, then the forces are balanced. So when I have this applied force of 344, then my friction force is not going to be 400, right? It's the less than or equal to. So in this case, that would be less than. So it's only going to push back with a friction force of 344. And that is absolutely true. But the reason B is wrong is this is saying that the static friction force would have a magnitude of 344. Yes, that is true. But they're saying it's guaranteed as reaction force by Newton's third law. That's not what Newton's third law is saying. Newton's third law is saying if I have an applied force of like whatever it is, my hand on this box of 343, that means that the box pushes back on my hand at 343. Not that the friction force has to equal the applied force. That is not the same two pair of objects, so it's not necessarily the same force. In fact, it is very possible for me to have an applied force of greater than the friction force, right? We have that all the time when you accelerate something. The applied force is greater than the friction, so that is not true because this part is not true. Number 4, we've got a light string and it's pulled to the right by a second string so that they accelerate frictionless. We want to know what the tension in T1 is compared to the tension in T2. So draw a free body diagram, T1, this one has T2 minus T1. So F net, which is just 2ma, is T1. F net here, which is 3ma, is T2 minus T1. And then I want to know what T1 is, but I don't want A in my answer, so I'm going to take this, substitute it in over here. So that's going to be T2 minus 2ma is 3ma. Add that over, that gives me that T2 is 5ma. Now, if T1 is 2ma and T2 is 5ma, and I'm looking for what T1 is compared to T2, well, I know it's less. And specifically, if you're looking at your factors, it's 2/5 less. Now, if you're like, where did you get 2/5 from? So basically, this is saying this ratio right here is if I divide T2 over, see how that's just a ratio of T1 over T2? Well, T1 is 2ma, T2 is 5ma. So see how the ratio of T1 over T2 is just 2/5? So that means T1 is 2/5, multiply this up, of T2. Most of you just look at that and you're like, oh, this one's 2/5 of that one, so if you multiply this by 2/5, you get 2ma. Alright, number 5, a ball of mass m is falling towards the earth. We are comparing how much the earth pulls down with this force and how much the ball pulls up on the earth. So if you'll notice, we are talking about the force between the earth and the ball compared to the force between the ball and the earth. I know that the earth pulls down with the force of mg on the ball, so I'm wondering what does the ball do to the earth? Well, I have two objects. Object 1 on object 2 compared to object 2 on object 1. That is literally the same force because, right, if I call this A and B and this one would be B and A, doesn't matter what they are, what the two objects are, it doesn't matter what's happening, whether it accelerates or not. In this case, I am not arguing that the ball does not accelerate, right? I'm not trying to say that there's another force on the ball pushing up equally as much. The ball could have just gravity. It doesn't matter if there's air resistance or not. What I'm saying is between, obviously not to scale, between the ball and the earth, they are pulling on each other with the same force. So the force of this one on this one is the same as this guy and this guy. So it is B because you are literally talking about the same pair of objects, so it is the same force, it is the force between them. 6, we've got a 50 kilogram block at rest, we've got friction, and we're going to apply a 260 Newton force. So because it starts from rest, I need to check what is my maximum static friction. So that's going to be mu s times the normal force. Here, gravity is just going to be 500, so my normal is just 500, and then my static friction is 0.5. So that gives me 250 newtons. So that is my max static friction. That is the friction force that I have to overcome if I'm going to move. I'm pushing it with 260. See how I'm pushing it with greater than the static friction? Well, my static friction can't be more than 250, so that means that it's going to move. And then once it moves, now it's going to have kinetic friction, which is 0.35 times 500. I actually don't know that one. So that's going to have a friction force of kinetic friction of 175, and then still an applied force of 260, so for sure this is going to accelerate, so it accelerates to the right. We want an expression for the applied force. I'm looking for F applied. To keep an object of mass m at a constant speed. As soon as you see constant speed, that means balanced forces. And F net equals 0. So if you have F net equals ma, well actually your acceleration is 0 here. It's not accelerating since it's at a constant speed. That should be 0. And we've got static versus kinetic friction. Well, here I said that I want to keep it moving at a constant speed, so that means I'm going to be using kinetic friction, not static, because I'm not starting from rest. Alright, so free body diagram. We've got the force of gravity, balanced out by the normal force, because it's all on some surface, horizontal surface. I've got some applied force. And this one, I do have friction. It's going to be kinetic friction, and it has to be exactly equal because it says that it's constant speed, which means these are going to be balanced. Now, some people go to F net equals FA minus FF, and then what they do is we replace F net with MA, but we already know our net force is 0. We know that these are balanced, so why don't we just jump to these are the same force. Force of friction equals FA. And you can say the same about up and down, because it's balanced up and down, so Fn equals Fg. Now I can replace Fn is just mg then, and Ff is mu Fn to get my applied force. And lastly, I want to substitute mg in for my Fn, so mu mg equals F applied. And I want to use like the gibbons, right? So it's either mu s or mu k. We already said that it was mu k because it's moving, so mu k mg is my applied force. A box of 2m is on top of a box of m. So this is my m, this is my 2m right here. The elevator is moving upwards and getting faster, so that means acceleration is up. So all my forces, I'm going to put a note right here, acceleration is up, so all my upward forces must be greater than the downward for each object. I've got F floor is the force between the floor on the bottom box, and F box is the force on the top that the top exerts on the bottom. So I'm going to break this down. Draw a free body diagram for both. Obviously, they both feel their own force of gravity. That's easy. This one would be longer. That's okay. Now, the force of the floor, if we look at our diagram, only one box is touching the floor, so only one box can even feel the floor at all. It's box M. It's box M. The floor is going to be pushing box M up, so F floor, like this. And then F of the box. So it says F box is the force that the top box exerts on the bottom box. So if you think about the 2m on the M, the 2m is pushing the M1 down, so this would be F box, like this. Now, that is how much the top box exerts on the bottom box. So if I'm thinking about what does the bottom box exert on the top box, well, top, bottom, bottom, top, it's the exact same two objects as the force on one another. So then that is the same force, it's just that the bottom box pushes the top one up, equal and opposite. So this is F box right here. And then now we have enough to write our net force equation. So this guy's net force, it says I'm accelerating up, so this one is greater, is F box minus Fg. And this one is F floor minus F box and also minus Fg. Some people still do the minus these two together, it doesn't matter. Now I'm going to replace F net is ma, Fg is minus mg, F net here is 2ma, and Fg here is 2mg because it's mass times gravity, and my mass here is 2m. Alright, now I'm trying to find F floor, so I'm going to use this equation, but I'm not allowed to have a box in my answer. I'm allowed ma and g, so that's fine, but I need to replace F box. So let's get, oh, that's a minus sign. Let's get F box by itself, add this over, that's 2ma plus 2mg is F box. And then now we're going to substitute this in for F box. Minus F box, so minus all of this. minus mg. So let's distribute. This is F floor minus 2ma minus 2mg minus mg is my ma. This would just become minus 3mg, minus 3mg. Trying to get F floor by itself, so I'm going to add this over. That becomes 3ma is F floor minus 3mg. And then lastly add it over, so 3ma plus 3mg equals F floor. And that would be your answer. Very, very similar situation, except for now I'm in an elevator that is moving upwards and getting slower, so that means my acceleration is down. I still have the same free body diagrams, right? I haven't changed the forces. It's still the floor pushing up and then gravity on each of them, and it's still the bottom box pushes this top box up and the top box pushes this bottom box down. It's just that now it's not accelerating up, so these upward forces are less than my downward forces. I'm just going to redraw pretty much exactly what I just had. It's just that my bottom forces win, so I'll put F floors less F box. So something like this. Now I'm writing my net force equation. It's the same forces, but now, same forces, but now I'm going to be doing the bottom minus the top because my bottom ones are greater. So this would be Fg minus F box, and this one would be F net is F box and Fg, both of these minus F floor. Now we're going to replace. This one was my 2ma equals 2mg minus F box. This one is ma equals F box plus mg minus the floor. End goal is I want to find the floor, but first I would need to get the box by itself. Two ways to get box by itself. You can subtract this one over, but that's what negative F box is, and then you would have to divide by negative, so flip the signs. That is totally valid. What I did is, because some people get confused with the flipping the signs, is I just added F box over here. And now that is F box plus 2ma equals 2mg. And then now it's really easy. Subtract that over. F box is 2mg minus 2ma. And now when I have that, I'm going to substitute that in here. So now I've got ma is F box, which we just said was 2mg minus 2ma. Plus mg minus F floor. I'm going to combine these, make that just 3mg. And then I'm going to add that over and make that 3ma is 3mg minus F floor. Now, you could do like I did over here, add floor over, subtract this over. That's totally fine. I'm going to show the other way just so you see an example. You could subtract this one over like this. That's 3ma minus 3mg equals negative 4 because they did not get rid of that negative sign. So then you're going to need to divide by negative 1. So when you do that, you just flip the sign. That's negative 3ma minus, oh sorry, now that is a plus because you flip it, plus 3mg is F floor, which is your answer. Now most people would have 3mg minus 3ma. Here, it does not matter, it's the exact same thing. It's also what you get if you were to add this one over, add this one over and subtract the 3ma over. It's the exact same thing. Notice this one is different than this one. Here, my floor is my gravity force plus my upward net force you can think about of the system with the acceleration. Here, it's my gravity force minus what the net force on the system is to get the missing floor. 10, we've got boxes M1 and M2 connected by a string and accelerating upward with a force Fa. So it's dropped there. We're ignoring air resistance, so free body diagram. So first of all, they should both feel their weight for sure. This is one where I'm actually looking at the grid didn't show up, but looking at the length. So M2 should have a greater Fg. Just slightly greater is fine. Let's draw the free body diagram. No, that's fine. So M2 feels this tension force. I'm going to call this force right here tension. So F2, I'm going to draw this tension force like this. And it's going to be greater than the gravity force because I know that I'm going to accelerate up. Now M1 feels this applied force, but it also feels tension pulling it down. It's the exact same tension, so you need to make sure that this tension length is equal to this tension length. And then lastly, M1 feels this F applied upwards, and you need to make sure that this is greater than these two combined, which looks like mine is. Now we can write our net force equation. Oh, that's not Fn, that's definitely F applied, sorry. There is no normal force because it's not on a surface. This is F applied minus both of these, so minus Fg minus tension. Here, this is just tension minus Fg. Now I replace F net is mass times acceleration. This one was m2, right? My mass is not m, it's called m2 here. Tension minus m2g. This one is m1a equals Fa minus m1g minus tension. Get tension by itself, that's m2a plus m2g. Now I can substitute this in. M1a is F applied minus M1g minus all of this. So that becomes minus M1g minus M2a minus M2g equals the M1a. Now, it's tempting to divide by M1 to get a by itself, but I actually have an a over here, so you have to combine all your terms with a first. So I'm going to add this one over. That gives me M1a plus M2a. Is Fa, right, I've moved that over, minus M1g minus M2g. Now here, these both have a, so what I need to do is I need to pull the a out front, and that's going to give me A1, or M1 plus M2 equals this, has not changed. And then last is I divide this term over. So I have Fa minus M1g minus M2g all over M1 plus M2, and that is my acceleration. Which kind of makes sense because it's my upward force minus both of these weights divided over both masses to get the acceleration of the system. Here, I again have an acceleration. I'm looking for the missing force. So I've got F, I've got Fg, and I've got tension. And then this guy's got gravity and tension as well. So net force is F minus Fg minus T. And then the other net force is T minus Fg. This one's easy, it's Ma minus Mg. And then this guy is 3Ma equals F minus 3Mg minus tension, right? Because it's mass times gravity, which is mass of 3m times gravity, so 3mg. I need to substitute in for T, so let's add this over. Ma plus Mg is T. Plug in. Minus all of this. So minus Ma minus Mg. So that becomes negative 4mg. Add this Ma over, that becomes 4Ma. And then I'm trying to get F by itself, right? Determine expression for F. So then you just add over 4Ma plus 4mg is your F. M and 3m are accelerating horizontally. Friction is negligible, which means you don't have to worry about it. You can ignore it. So here we've got, well, of course, the force of gravity and normal are balanced, and both of them. This is a smaller force of gravity, which is also balanced with its own normal force. This guy feels a force F that's some applied, and then I'm going to call this string force tension. And I know tension is less than the force applied because I know it's accelerating this way, and these two have to have the same tension force. I'd be checking to see if those are the same lengths. So the net force is just F minus T. This net force is T. Now I replace, this one was M, so Ma is T. This one has a mass of 3m, so it's 3Ma is F minus T. T we can just substitute in. This T is Ma. 3Ma is F minus Ma, add over, 4Ma equals F. I'm looking for acceleration, so A is F over 4m. Now, I'm asking you to include friction, so I'm going to redraw my free body diagram real quick. I've got tension, I've got this applied force, right? I haven't changed that. All I'm doing, and this should be roughly the same, all I'm doing is I'm saying these now have friction. So friction, if it's trying to move this way, the friction is going to be against it in each case. Fg, Fn. So then my net force equation here is not just T anymore, it's T minus force of friction. My net force here is F minus tension and minus this friction force, or you can think of it as minus both of them together. It's the same thing. Now I'm going to replace, so I'm going to start with F net. So F net would be Ma This F net would be 3 MA. T minus force of friction is mu Fn. And F minus T minus mu Fn. Now let's go ahead. On this guy, Fg is just mg, so this Fn would be mg. So this is just going to be mu mg. Like this. This guy's Fg is 3 mg, so its normal is 3 mg. So then I'm going to replace normal with 3 mg, so this is mu 3 mg. Okay. Now I'm looking for acceleration. I'm allowed to have m, f, mu, and g. So I'm allowed all this, I'm allowed this, I'm allowed that. It's just t I need to get rid of. So let's solve this guy for t. So add over, you have ma plus mu mg to get your t. Substitute in. This is f minus ma plus mu mg minus t minus mu mg to get my ma. So I'm going to get my 3 MA, sorry. I'm going to add this MA over, which is 4 MA. F minus, make sure you distribute this negative to the mu mg, minus T minus mu 3 mg, that's a 3 in there. And then mu mg and mu 3 mg, well, those are the same, it's just this one has a coefficient of 3, so that would be minus, not tension anymore, oh my god. I just substituted in for the tension. Right, I don't have T anymore, I just substituted in minus the mu 3 mg, my bad guys. So I can combine these like terms, mu mg minus 3 mu mg is just minus 4 mu mg to get your force minus that is 4 ma. And then last step is divide to get A by itself, so A is F minus 4 mu mg all over 4m. You would not cancel out the 4m because the F does not have a 4m, so those can't just cross off. And lastly, we want an expression for the force needed to push the falling blocks at constant velocity. I would, as soon as you see constant velocity, I would think like, okay, balanced forces. When you draw your three-body diagram, they should all be equal. So I'm going to call, it told me to call this some F. I know that there's friction. I also know that there's some force between them, so I'm going to call this F box. So let's draw our free-body diagram. We've got Fg and Fn. Got Fg and Fn on this guy. This guy feels the force F for sure. Let's do the box force. So the 2m is going to feel this box pushing it to the left, to the right, sorry. That's F box. And then this guy is going to feel this one pushing against him, so that's to the left, F box. And then it says that there's friction, so I know that these both feel friction against it. These would be equal because it says balanced. And then these two together balance out this one. So when I write my F net equation, I'm actually not going to write F net because my net force is 0. I'm just going to jump to these two are equal. F friction equals F box here. Here, F box plus F friction equals F. Now note, these are not the same friction force because they have different normal forces, right? So I'm going to go through. Fg here is 3 mg. This one is 2 mg. And then it's balanced up and down. It's not accelerating up or down, so those are the normal forces. So when I plug in F box, friction force is mu Fn. I'm plugging in F box plus mu. Fn here is 3 mg to get force. And then here, my mu Fn to get my F box. Fn for this guy is 2 mg. So mu 2 mg equals F box. And then now that I have F box, you can substitute this in. So that's mu 2 mg plus mu 3 mg equals force. And then add them together, that's 5 mu mg is the force needed. If you have questions, come in the morning, please.